Hello everyone, my name is Wang. I'm from Michigan State University. I am very glad to present our paper, Sequence Learning with Site Dependencies. This paper is co-authored with Dr. Hui Liu from Michigan State University, Gail Huang from Tile Education Group, and Zitao Liu from Tile Education Group. In this talk, I will firstly give a brief introduction of the background information, and then I will describe our proposed framework. Then I will demonstrate the experiment and their analysis. Lastly, I will conclude the talk and discuss possible future works. So let's begin with the background information. A sequence is an ordered list of elements. This figure shows an example of a sequence. It contains three types of elements that are denoted as 1, 2, 3. These elements are arranged together with a specific order. Such sequential data are ubiquitous in real world. For example, the log records of a computer system, online transaction in a bank system, and the genes in the bioinformatics, and of course, natural languages. Therefore, a large amount of effort has been devoted to modeling sequential data and have achieved great success. The most popular sequence modeling methods are recurrent neural networks such as LSTM and GRU. This figure shows a vanilla RN structure. It processes the elements sequentially. Thus, it naturally preserves the order information of the sequence. Due to its effectiveness in capturing sequential dependencies, they have achieved a great success in a variety of fields, such as language processing, knowledge tracing in education, and session-based recommendation systems, etc. However, elements also exhibit site dependencies. So what is site dependency? Here, I use a toy example to illustrate. As we can see in the left part of the figure, there are three sequences that consists of four types of elements. And from the side part, we also know that there are connections between elements. In other words, these elements are not independent. Actually, the scenarios shown in this toy example are commonly seen in real world. For example, in session-based movie recommendation systems, movies are not independent. Movies which are directed by the same director may have similar features. In knowledge tracing scenario, where we want to model the knowledge state of a student based on her historic interaction with questions, the question that requires similar skills are naturally connected. So previously we have shown that sequences with set informations are really common. A natural question to ask now is, why are they important, and why do we start the site dependencies of elements? Next, let me use the knowledge tracing as an example to illustrate. In this example, a student has involved three sequential events, which is denoted as x1, x2, and x3. Each event includes the question the student answered and the correctness of the answer. Specifically, the student firstly solved the question B, but her answer is not correct. Next, the student answered question A and C correctly. Now if I ask whether the students can answer the question D correctly, you probably have no clue. But if we know the site dependence of questions as shown in the figure, we know that she is likely to get the question D correctly, and C, A, D are closely connected. So in a summary, site information is complementary to the sequential information and can play an important role in sequence learning. We have demonstrated the importance of capturing set dependencies of elements for sequential learning. Next, I will introduce a proposed model that can achieve this. Before that, let me formally define the problem we want to solve. In this work, we focus on user behavior modeling tasks where labels are the user actions on a given element. As the figure shows, assume we have k user behavior sequences in the training set. At each step of the sequences, the user will act on one element. In addition, we are also given the element graph that describes the connections between elements. With this, we aim to build a model so that in testing stage, when given a sequence, it can predict the user action on the element in the next event. This is an essential task in a wide range of real-world applications. For example, in recommendation, this task is equivalent to predict the actions of users on the next recommended item. And in education, it is a task of knowledge tracing that aims to predict whether the students can give the correct or wrong answer to the next question. In the next section, we will describe our proposed framework to solve this problem. Here is the overview of the proposed framework. As I mentioned previously, there are two types of information that can play an important role in sequence modeling. The first one is the sequential dependencies, and the second one is the set dependencies. Thus, in order to incorporate these two types of information, we designed two major components in our framework. The first is the sec block, which focuses on capturing sequential dependencies. It takes a sequence as an input and output the representation that capture sequential dependencies. The second is the set block. It takes the element graph as an input and output a refined representation for each element. In addition, the framework also has a prediction layer that takes the outputs of both blocks and predict the user action on a given element. Next, I will give detailed description of each component. The first is the sec block. It consists of two types of layers that are input and sequential layers. For input layers, we designed this layer to embed event information into a dense vector. Specifically, each event contains three types of information that are element information, action information, and the position information. So we first design an embedding matrix to embed the element in a latent space. Then we concatenate the embedding with zero vectors to incorporate label information. Lastly, we add the widely used position embedding to the previous vectors. With the representation of each event, next, we describe the sequential layer to obtain the representation of the whole sequence. The sequential layer consists of a attention sublayer and a feed-forward sublayer. Specifically, the input of the sequential layer is the sequence of event representations obtained from previous input layer. These inputs are firstly processed by an attention sublayer that employ multi-head attention operations and can effectively capture the sequential dependencies. After that, a feed-forward sublayer is designed to refine the representations. These two sublayers are connected by a layer normalization and a residual connection. Finally, the layer will output a representation that captures the sequential dependencies of the elements. Now I introduce the set block that will incorporate set dependencies of elements. The set block consists of two types of layers that are linear and aggregation layers. To illustrate, I will use the JS element as an example. The input of the linear layer is the initial element embedding vector, which is denoted as EJ. This vector can be obtained from random samples or graph embedding algorithms. We have explored both ways, and I will introduce more details in the experiment part. The linear layer is project embedding into latent space that are optimal for site dependency learning. Then we design aggregation layer to incorporate set dependencies. The goal is that the connections between elements should also be reflected in the element embeddings. To achieve this goal, we first conducted a nonlinear transformation of the element embedding. Then we obtain a new element embedding by aggregating its neighbor embeddings. Here, Nj is the neighbor set of the element J, and A is a normalized adjacent matrix. Finally, we concatenate the original and the new element embedding to obtain the refined embedding of the element. Previously, I have described two major components of the proposed model, C. In this slide, I introduced the prediction component and the objective function. To recap, the site block will obtain a representation of the whole sequence that captures the sequential dependencies. The site block will output a refined element embedding that incorporates site dependencies. Now we query the embedding of a specific element that is shown in the next step of the sequence. Then we conduct a dot product between queried element embedding and the sequence representation and input it in the sigmoid function that will output a value indicating the probability of the action label being positive. Therefore, to get the learning process, we use the cross entropy as an objective function. Furthermore, to take the average of the action label in each position of the training sequence, we use the truncated back propagation through time algorithm to train the framework. Now I have introduced our proposed framework, which is called C. Next, I will describe the experiment we have conducted to validate its effectiveness. In our experiment, we evaluated a framework with two real-world datasets. The first is the GMAT dataset. This dataset describes students' interactions with GMAT questions that are designed to improve the students' problem-solve skills. So the element are the GMAT preparation questions, and the label is whether the students give the correct answer or not. The second dataset is the moviness dataset. This dataset describes user rating behaviors for movies. So the element are the movies, and the labels is whether the user liked the movie or not. We compare our proposed framework with three types of most popular neural networks that are RNN, LSTM, and GRU. In addition, for each method, we explore two ways to obtain the initial element embedding. The first is to randomly draw from Gaussian distribution. The second is to use graph embedding algorithms such as 9, and we denoted these two methods as Gaussian and 9 respectively. For evaluation, we use AUC as the matrix, and the higher the AUC is, the better the performance. Here's the experiment result. From the figure, we have several observations. First, in most cases, RNN has the worst performance among baselines. This is because LSTM and GRU has gating mechanism, which enable them to capture long-term dependencies. Secondly, for most cases, the line has much better performance than Gaussian, which clearly shows the contribution of element set dependency information. Third, in all the cases, the proposed model C demonstrates performance gain over baselines by a large margin. We attribute such superior performance to its ability to effectively capture both sequential and site dependencies of elements. Finally, let me conclude this presentation. In this paper, we have identified the importance of capturing set information for user behavior sequence modeling problem and propose a very effective model, C, which outperforms representative baselines significantly. So in the future, we would like to explore set dependencies for other sequence learning tasks, such as language modeling. And another meaningful direction is to utilize our proposed framework to address code start and data sparsity problems. Thank you for your listening.